Okay, let's start, right? So my name is Anmol Darak. As you know, we have in my one of my previous videos, I was talking about deep sets problem. The title of that video, you could see something like the ML problem nobody talks about. Actually, nobody actually talks about. So there is one interesting problem statement, that problem use case, right, that I came across. So which we are kind of trying to which will try to solve it. Okay, so I'll start from the problem statement, explain you what that problem is, and then we will see how ML model can be used there to kind of predict what we want to predict. Okay, so so first thing that we are looking for is problem statement. So what is the problem statement here? The problem statement here is that, let's say there are two patients, patient 1 and patient 2. Okay, so patient 1, let's say they went to 4 people for showing their problem and getting it resolved. Okay, what is the problem? Let's say that problem is X, and let's say this problem is Y. The problem could be anything. Okay, so this is something we will talk about that later. Okay, so let's say this is the problem X. Now what, let's say the patient 1 is solved by, let's say, 4 personas: P1, P2, P3, P4. Okay, and what is P1 is? P1 means P1 is the first person who, so these all people actually are responsible for treating this patient 1. Okay, and let's say there is another patient, that patient, let's say there is one more person. Okay, so there is one more person, which let's say P5, who is treating this particular patient. Okay, and let's say these 4 people, we call them, we actually, each persona has, let's say each persona has what is their level, like whether they are senior, junior, what is that, what is the role, what they do, right? And then which specialty they are in. Okay, so usually they are doctors, so they have some specialty. Some could be nurses, some could be pharmacists, some could be just physicians, something like that. Okay, same goes with the patient 2 as well. We have level, role and specialty of that person who has helped in treating this patient. Okay, these 4 people actually were treating this patient, and this one was treating the second patient. Okay, so first, who was, let's say, just as an example, let's say senior. Okay, senior, and then surgeon, senior surgeon, cardiologist. Okay, so that is the first person. Okay, let's say the second person here is ICU. Okay, ICU nurse. So this is just some dummy example. I am looking at the screen for referring to this. Let's say this is critical care. Okay, critical care unit, and this is senior. Okay, senior, and pharmacist. Okay, oncology. Okay, so this is the third person who has attended this particular patient and helped in their treatment. And then resident, physician, internal med, something like this. Okay, so these are some values of the these are particular special, like level, role and specialty of the people who have tried to kind of attend this patient for helping them in their problem, in recovering their problem X. Okay, and this is, let's say this is intern. Okay, their level is intern, and they are, let's say, physician, right? And then there, let's say this is general, their category is general, the specialty is general. Okay, let's say now, given this, now let's say this patient has recovered. Okay, let me just use a different pen here. Recovered fully. Okay, this person did not recover. Okay, so there are 2 patients that recovered or not recovered. Okay, now given this, let's say I want to know. Okay, so I have one more patient which says, let's say there is a third patient, patient 3. there is a patient 3. Okay, so this patient actually, okay, we let's say there is a p5, p7, p8. Let's say this is p6, not p5. Okay, p5 is here already. So p6, p7, p8, he went to p6, p7, p8. Okay, now we want to know what is the probability that he will recover if he went to p6, p7, p8. Probability of recovery, what is that? Okay, so here we are going to use a ML model. So that is the whole crux of this problem. So we want to know, let's say if I have p6, p7, p8, these are the personas. What is this called? Personas. Okay, so personas means what is the level, role and specialty. So each p6 has got a different level, role and specialty. p7 has got a different level, role and specialty, and p8 also has got a different level, role and specialty. Okay, so p6, p7, p8, these three people have helped, were involved in treating the patient number 3. Now we want to use machine learning model which will predict, given these three people have helped patient 3 in their recovery, what is the probability of the recovery. So that is what we are trying to find here. Okay, this is now this become very interesting problem, right? We have lots of this data. Which data? This data, this particular data, this data and this data in the historically, because we know at different points of time what patient went to what kind of persona, and at that time whether they were recovered. So using that we have several of these historical data. Okay, so now we want to create, train one machine learning model which will predict this, like p6, p7, p8, given this, what is the probability of the recovery? How would we do that? Okay, so that is the main problem here. Okay, so the thing is, in this problem, if you see this carefully, right, so for patient 1, right, for patient 1 we have p1, p2, p3, p4 who have attended this patient, and they have taken the treatment, but they recovered, actually recovered flag, right? This is like a target variable for you, right? And this is like input or independent variable, whatever you call, right? For patient 2 you will collect data like this, right? You need to collect the data, right, for preparing the data ready for your training the model. So let's say this is p5, right? They did not recover means 0, they recovered means 1, right? That's how you will keep on adding the data. Let's say p3 is there, they were taken treatment from p6, p7 and they got recovered. Let's say patient 4, right? Let's say they have they it's the same p4, same persona, but let's say p8, the second one, and they did not recover. Okay, and so on, right? Patient 5, let's say p9, p10 and p11, they recovered. So you have like several of this data historically. Now you want to use this data, okay, to kind of, but remember, each persona is a combination of level, role and speciality, right? Now you want to use this data to train a machine learning model that given any patient's persona, whoever has attended that particular patient, given that, how you need to predict the probability of the recovery. That is the problem statement. How would you do this, right? So given this data set, right, this is how you can think of this. Next, how would we do this, right? So one thing that comes to mind is we can convert this, because we need to convert this into numbers, right? It will not, the machine model doesn't any machine learning model needs to be converted into numbers first, right? So from this, because these are all characters, you can see these are characters. So usually what happens is, in a classical machine learning model we have same number of columns, right? We have like fixed number of columns, like 50 columns or 100 columns or 500 columns, and there is a target variable on which we can simply do some, like we follow some steps, like data cleaning step, like checking missing values and so on. We do all that step and we kind of do feature selection, like feature elimination, like bad features, like low performing features we eliminated, keep very good high performing features we remove, call in narrative, blah blah blah, we do all those stuff and train the model, and then you kind of do that. But here in this case it's not that case, right? So you have like varying number of patients, so personas, right? So for patient 1 there are 4 people involved, the patient 2 there is only 1 person involved, right? Therefore patient 3 there are 2 personas involved, and so on. Okay, so there is different number of people involved, and here you need to kind of, in order to solve this, we need to somehow convert this into fixed number of columns or something like that, is what we need to kind of think about it. So how do we do this, right? So how do we do this is, let's say, and even before that, right, each persona will has 3 separate things, right? Level, role and specialty. How would we solve about this, right? Let's now think about this. So what we can do is, one way we can think of is, we can convert this persona into some embedding vector, right? So there are so many transformer models or whatever you use, right? So convert into embedding vector. But you convert this one into embedding vector or this one into embedding vector, how do you convert this, right? That's the problem, that's main problem, right? So one way to deal with this is kind of converting, but we need to find out a way where we can kind of bring all of these together into same number of columns, so we can fit a machine learning model there. So what we do is, we kind of find out level, right? Level, role and function. So speciality, what is that, whatever you call it, speciality. Level, role and what do you call speciality. Okay, so level, role and speciality, right? So in this particular problem, so let's say there are some 10 distinct levels, right? So usually it is not 10, let's say there are only 3, right? Let's say 5, right? Junior, senior, super senior, right, and something, right? So let's say this is L1, L2, L3, L4, L5. There are 5 distinct. And same way, let's say there are R1, R2, R3, like one is surgeon, one is physician and so on, right? R5, so on, R6, so on up to R, let's say 20, right? Specialty, let's say there are multiple specialties, S1, S2, S3, S4, so on up to S25. So total number of combinations is 5 into 20 into 25. This many number of personas. Okay, so this many number of personas, and there could be more, right? There could be more. Okay, so we need to understand how we can solve this problem, so we can extend this to any use case of similar problem, right? Similar use case, right? So that is what we are trying to understand here. Okay, so what we will do is, we will kind of use this each of these and convert into embedding vector. Okay, so each one, L1, let's say we convert into a 32 dimensional embedding vector. Okay, same L2 32, L3 32. What does this mean? This means numbers, right? 0.35, 0.18 and so on, right? Same goes with the others as well, right? So L1, L2, L3, so on up to L5. Same goes with R1, R2, right? R3, so on up to R20. And same goes with S1, S2, so on up to S25, right? So you will have 32, 32, 32 each, right? So now what we do is, we again coming back to this problem. So okay, so we have some mechanism to convert this L1 into embedding 32 dimensional vector. Okay, and all R's, which are roles, and all specialties S1, so on up to S25, all of them we kind of convert into numbers, embedding vector, proper embedding vectors. Now what is now how do we use this, right? Let's say we got that mechanism, we converted that. Now how do we use this, right? So let's say we take patient 1, we have 4 people treating them, right? 4 personas treating them, right? So first persona is this persona 1, persona 2, persona 3, persona 4, right? For P1, let's say we got, this is level, role, specialty. Okay, so for low level, for let's say that was L1, we will have 32 dimension vector, right? Means 32 numbers here, right? Same goes with whatever role is, let's say this was R1, let's say, so we will have that 32, right? 32 dimension, and so on. For events goes, same goes with the specialty as well, right? You keep on doing this, right? 32, 32, 32, right? 32 dimensions numbers, right? So once you have all of these, okay, 32, 32, 30 means 96, right? So for patient 1, you will have 96 numbers, 96 numbers, 96 numbers, right? Now let's say patient 2. Patient 2, what do you have? You have only 1, P5, and patient 3, 2, right? P5, 32, 32, 32, and there is another patient, patient 3, and so on, right? Sorry, P6, P7, let's say this is again 32, 32, 32, so 96 overall, right? 96, this is also 96, this is also 96. Now you have 96 numbers. The main thing is you have varying number, right? P4, P4, P5, P6. That is where we will solve this problem using a method called padding. You might already know this concept, but the thing is it is slightly different. We will try to solve this in a slightly different manner. Okay, so what we do is we have this 96. Okay, we 96 numbers, take 1% of the first patient. Okay, so patient 1, we are talking about the patient 1 itself. Right? So we're talking about the patient 1 itself. Patient 1. So in this patient 1, and let's say take P1 only in that. Okay, in that P1 we have 96 numbers. Take those 96 numbers, pass it through a neural network, because we have some numbers, no fixed numbers, right? For P2 also we have 96, so which means we have some fixed numbers where we can actually start the things from. So 96, so you have 96 nodes. This become your input layer, right? Then you apply, because this is a neural network, right? So you have second layer, right? So let's say you keep some 128 units here on nodes, whatever you call it, hidden units, right? So 128, so which means this 96 into 128, so you have, this is all fully connected layer, right? So this is fully connected layer, so which means the output of this is going to be 128 numbers, right? Same thing goes with the P2 as well. Same thing goes with the P2 as well. Okay, same thing goes with the P2 as well. So for P2, we actually kind of try to for P2 we kind of do the same thing. We get 128 numbers. Okay, so for P2 also we get 128 numbers, and so on, right? So we get 128 numbers. Okay, so because neural network, we see that there are multiple layers, we kind of add one more layer. Okay, so let's say we add one more layer here. Okay, why do we add it? To probably kind of increase the accuracy of the model. Okay, so let's say we have added that. Okay, 128. Okay, so we have kind of added that. Okay, so this is again a but fully connected layer sometimes might create overfitting problems. Let's say I added dropout here. Here also I added dropout. Okay, I added a dropout here now. Okay, now what will happen is, in the end, even after you put like a 128 here, you will still end up with a 128. So remember, 96 went through 128, there is a dropout in between, and then 128 again, and there is a dropout in between. Correct? So for all, so which means for patient 1, PT1, for person of 1, we have 128 numbers. Same thing goes with the other personas attending this particular patient, 128, 128, and so on. Okay, finally, even after dropout is not going to reduce the number of dimensions. Okay, so it is going to just remove some of these connections and make them value equal to 0, which means that 128 still remains same, right? Here the weight, some of them, they kind of removes it, right? So which means you will still have 128. So now the thing is mask, right? So we use a concept called as masking. Okay, so even before that, okay, now since these are 4, okay, padding we have told, but we did not tell what is the maximum length of the padding. Okay, how do we find out maximum length of the padding, right? So here there are 4 personas, another, there is only one persona, there is another 2 persona. What we can do is we can look at all the historical data, and we can see for each patient how many number of people, how many number of personas attended. Let's say in the first case it was 4, PT2 there are 1, PT3 there is 2, right? And PT4 let's say some 7, and so on, right? You will have this data. Let's say the max of this column is equal to some, let's say 20. Okay, sometimes the data might have some outliers, right? In that case it might go 130, right? You can consider 95th percentile and safely consider some number. So you can pad the data, which padding means, let's say for the patient 1, what you can do is simply for the patient 1, what you can do is simply you can simply kind of use so for the patient 1, this is patient 1, you can do P1, P2, P3, P4, so on up to P4, right? Only then you can add dummy. You can imagine dummy as their level, role, because each one is having level, role, so even the dummy should have, right, level, role, and speciality. You can have something like dummy values. Okay, so and even for these dummy values, you can imagine some 32 dimensional vector, obviously, right? Usually dummy, you can see there is some special token, something like that, if you know about transformers, right? So they also have some embedding vector. So similarly, even for the dummy, there is a embedding vector which are all non-zeros, right? These are all non-zeros values, so this will also have 96, right? Like that you will have 96. Okay, so but this one also would go through the same network, and same network, so this one also would go to the same network like this, and you will end up with 128. Okay, same 128 numbers for the D, this D. How many D's like this? You can simply have you can simply have 17 Ds. Why 17? Sorry, 16 Ds. 16 Ds. Why? Because maximum the padding length that you want is 20, right? 4 you already have, 16 you are adding dummy values, dummy personas, right? Why do you do this? So you can have uniformity there. So this is why you kind of, this is where you kind of pass this dummy also, and you get 128. So which means for the patient 1, PT1, P1, P2, P3, so on up to P4, then DD starts, and this will be 16. These are 16, these are 4, right? And then you will have 128, it will go through that network, right? Each of them will go through the network, 128 each. Okay, the thing then you would do is you will kind of sum all of these 128 numbers. Finally you will have this number, right, 128. So you will sum all these 128 numbers. So 128 numbers mean 128 dimensional vector, so you will kind of sum all of these. Okay, but remember, these are dummies, you cannot simply sum them up, you need to kind of convert these into zeros. Okay, so if you look at the dimensions of this, so first patient had right? First patient had four personas, right? And each persona had 96 dimensional vector, correct? But we added padding to this, so 4 became 6, right? 4 became 20 after padding, and this became 96 after padding, right? Then what this became, this had gone through that neural network, and this became 1 cross 20 cross 128, right? And then there was a dropout, and this was the first layer, right? And then there was a dropout, and then again it went to 1 cross 20 cross 128, and there is a dropout layer, so which doesn't change the dimension, 1 cross 20 cross 128, right? So but what we can do is simply we can multiply this with a mask vector or mask matrix, whatever you call it, of the persona. So which would look like this: 1 1 1 1 and 16 zeros, right? So this is a mask vector. Okay, so for each patient you will have this like this. Okay, there are only 4 ones, 16 zeros, 4 ones, 1 for each, representing each persona. When there is dummy, I need to flag those dummies, right? So this is how I am going to flag it. Okay, since these are 20 numbers, I can simply convert this into 1 cross 20 cross 1. I can reshape this. Okay, so previously I got this 1 cross 20 cross 20 128, and I have 1 cross 20 cross 1. So if I kind of do matrix multiplication, I will end up with 1 cross 128. Okay, what is this output? Why we do this matrix multiplication is because all these numbers that we got at the dummy places, right, these should not be added. Okay, this should not be added. Why are we adding, by the way? Why are we adding? We are adding it because all the information we want to be summed and kept it in a single array. All the information of all these 4 personas together combined and needs to be put in the form of an array. Okay, these dummies, since these are all non-zeros, if we keep adding these values also, the problem is that it will cause noise in the outputs, and that's why we need to mask this. And the way that we are doing that masking is using this particular vector. We could reshape that into 1 cross 20 cross 1, and which means that these zeros get multiplied with these values, and these become 0, and these non-zeros will be multiplied with these. 1 multiplied by any number is that number itself. So we will be summing all of this up, because we are doing matrix multiplication. These get summed up, so it gets summed up like this. So which means finally you will have 128 numbers. We cannot add these non-zero numbers. That's why we kind of multiply it with a mask vector, so dummies do not get accounted when we kind of sum all these up, right? So that is the whole crux of the solution, right? So now we have 1 cross 128. So 1 cross 128, once you have it, which means for each patient, this is at patient level now, because you multiply this 1 cross 128, which is this matrix. 1 means 1 patient, 20 means 20 personas, and 128 numbers. 1 cross 128, right? 128 numbers. So you have 1 patient, 20 personas, 128 numbers. So you kind of try to get this, right? So for each patient you get this 1 cross 128. Now you have a label 10 10. So each row is 128 128 128, right? So you have label. Now this becomes a classical ML problem. 128, fix a number of columns and fix number of rows, where you can use that for training any machine learning model. Since we are using neural network, we can go in one step forward, right? We can use these 128 values and into a, like, let's say another layer, 64 units layer, something like that, and then you can pass it to a 1 unit, where you can have a sigmoid activation function. The loss function that you will be using is binary cross entropy here. right? Because you have only binary label here, right? You can use a binary cross entropy loss function. So the loss will be calculated, and you can send this in 32 patient batch size equal to 32 patients going at once. So you'll have 32, so 32 patients and 96 units, then you have 128, right? 128, then you have dropout, then again 128, right? So like this, right? Then again dropout is there. You do this for each person, a P1, P2, P3, P4. Once you do this, then you kind of sum all this up, okay, even for D's, right? And sum all this up. How do you sum it? You kind of multiply it with the mask vector and then sum it up. You will get 128, and that 128 will pass into these numbers. That's how you can do it. Why 128? Why not 250? Yes, you can take 256. Why 32 only for each specialty role level that we do? You can take any number. You can take 55, 85, anything. Okay, you can experiment it with the different numbers. More number of numbers, more features you will capture, but you also need to think of, compute power that you have got. You do not have a lot of GPUs, and this problem might not require GPUs, right? So you can simply solve it to some problem depending upon the size of the data set you have and the use case that you are solving, right? Similar use case, you can solve the same, so using the same methodology. Okay, so that is the whole thing. Once you have this, that's it. So once you have this, you kind of simply train the machine learning model. After you have trained the machine learning model, you kind of need to predict it for the new patient. So how do you predict it for the new patient? Let's see that. Predicting for new patient. Okay, so how do you predict it for the new patient? Let's say you have a patient PT5, let's say fifth patient, and they are getting treated by P21, P31, P35, something like this, right? So when they are getting treated like this, so what you do is you kind of simply have 96, 96, 96. For all of them, dummy also you will have 96, 96, 96, right? You can simply pass it, and then for each of this person you pass through that neural network of 128, then 128, and then you get the find 28 values, and then you pass it to 64. But before passing, that's where the problem is, right? That's where the main thing is. You kind of sum it up. So you kind of pass it, you get 128 for each. P21 you will get, P31 you will get, P35 you will get, right? So you need to actually sum this up. For summing this up is where you can use that mask thing, because you don't need to worry about the dimensions and all. You can do padding and safely kind of do the sum pooling over all these values and get the final 128, which you can pass it to the next layer, which is 64, and then into 1, something like that, right? 1 unit, right? So that is the previous architecture. It's the same, like this is more of prediction, like inference part, right? Now then once you do this, whatever output you will get, value you get, that becomes your probability value. That is what you are interested in, probability of recovery. That's it, right? That completes this thing. But there is a second stage to this, right? So let's say the output of this, right? Let's say the output of this came out to be 0.35, which means 35% only recovery probability, right? Now I want to increase that. Okay, what other person I can remove? So not remove, or I because these are already kind of involved. What other person involved, as in all these where this patient has been attended by these 3 people. Now I want to add one more person, so the recovery probability kind of increases. So what I can do is, out of all the set of personas I have, I will try with P21, P31, P35 with all other combinations here. So P21, P31 and P35, right? I'll try all the combinations, P1, P2, P3, P4, which are not already there, right? P3, P4 and so on, right? I will try with all combinations, run the same thing. Okay, instead I will also add P1, P2, P3 right? Next person whom I should be persona whom I should be sending this patient, so their recovery probability could increase, right? That is what we are trying to find here, right? So that is once then I'll see for these four combination what is the predicted probability. Let's say that is p1. I'm using a lot of p, so let me just use something else. Okay, let's say that is small p1, small p2, small p3, small p4. I will see which of these is highest, right? Let's say p4 is the highest, which means this patient needs to be sent to this persona, so that the probability p4, let's say p4 is 0.85, right? Which means the recovery probability increased from 0.35 to 0.85 directly, right? So that is the whole thing, right? So what is the next persona to whom this patient needs to be sent through is what we are trying to find here. That is the whole thing. Okay, so now let's quickly get into the implementation part of this. So we can simply solve this using Keras. Okay, so this is what I will do. So I'm importing packages. I'm importing NumPy, Pandas, TensorFlow, Keras. So layers I need some regularizers. We will use regularization for kind of reducing the overfitting and all. So I'll use label encoder, because you see the personas and all, we convert that into label encoder, and then those will be converted to embeddings. Train test split, obviously for model training we need that complete class weight, because probably the model might have some, the data might have some class imbalance, which we will generate synthetically. Now we can see that how we'll generate, and these are all like performance related metrics and some matplotlib, so to kind of see how the visualization looks like. Okay, since we are going to generate the data, we will kind of use we will kind of use the some seeds, so we don't have to kind of worry on data generation part, like if we kind of we should be able to reproduce the data generated. Seniority levels, let's say there are these few seniority levels, there are 6 that are there. So, and roles, there are, let's say, like 7 roles, and specialties, there are these specialties. Let's say these are the distinct values that it has got. Okay, so now what I will do is I will synthetically generate some data where I will kind of kind of convert, create a score, and based on the score I will convert that into 1 or 0. So what I will do is, based on the seniority, right, if they have like a high senior, they are like a consultant and chief and all, like they will get higher score, and then this is like, you can think like I'm trying to generate like past historical data. Usually this is not how it is followed. We kind of use the real data, but obviously since we are learning, we do not have the real data. If you find some, you can actually try this algorithm on that, but for now I am going to use this particular based on seniority, based on the role. Okay, they kind of get some scores for based on, because they are intern, they got some low score, for example, because they're just starting the career, and the specialty score and so on, right? So based on different specialties, some of them, if they general like minus 0.5. So I'm just adding this, created this. It doesn't, I mean, like, don't take it otherwise intern, like some interns will be really good, some interns, so please do not take it yeah, otherwise it's just like a dummy data that I want to create to see how we can solve this problem. It's not against anyone. So I ran this, and then let's so what this is going to do is, it will take the team as in like who, like let's say there are 5 people, 4 people. We saw in the patient one example there are 4 people, right? So for each member we'll try to calculate the score, right? And based on the score we kind of keep on adding that score, because score is starting from 0. So we kind of keep on adding that score, and then that score kind of increases, like if the score is greater than some value, then we kind of clip it, right? Like in between 0.02, so we get the probability. Based on the probability we kind of, I think, will create this data set. So let's say if I want, so I am kind of trying to create this data set for a team, or for a number of patients equal to 3000. So I generate this data set. So I have data recovered and not recovered. So for 3000 iterations I need to generate the data. So I have, like, let's say 8 personas. So out of them, so these are like different probabilities of selecting all these one of these 8. So for each patient, let's say this is the team size, right? Number of personas attending that particular patient, right? So for each patient, so and we create that, and for each team we kind of take, like random seniority, random role, and random specialty, and then we kind of keep on appending the team to that, and we calculate the probability of that recovery. Okay, and then outcome is based upon binomial, this np dot random dot binomial 1 comma prob. So it's a binomial based on the probability. It kind of generates like some value, outcome 1 or 0, right? So then and then we kind of save this in the record. So we keep on saving these records, right? And then finally we kind of append the record to the recovered if the outcome is 1, otherwise we append it to the not record. And we kind of do like some kind of balancing here, like equal number of recovery and non-recovery, right? So 50-50. So why do we do this? We just to do this because we don't have to handle class imbalance. Class imbalance is a different problem, you need to handle it separately. So I just wanted to keep these things simple, just to focus on the core thing of this problem. So we generate this data and run it, right? So we kind of ran it, the data is generated. You can see like the data is generated right now, right? So yeah, now that the data is generated, now let's move to the next part, which is the encoding, right? So let's see, once the data, if you want to see, you can just check that, right? So this is the data, right? Import pandas as pd, you can just check this pd dot data frame. Yeah, so you can see recovered and all of that, right? So you check actually recovered how much percentage it is, 50%, you can see that, right? So it's a balanced data set, and you can also check the shape of this. So only 1222 rows. So we can now move towards encoding section. We can see what that means. Okay, so we'll move to the encoding part. So what we'll do is we take all the seniority for each team member, right? All roles and all specialties, right? So for the D in dataset, for each D in dataset, we kind of take this, right? And then we kind of run it. So for example, all seniority, we kind of then try to do label encoding. So we'll get label encoders for them, okay? And we also calculate the number of seniority roles. Why do we do this? Because we need to kind of create like we want to know like how many distinct number of seniority and distinct number of roles, distinct number of specialty are available. So then we also do max team size equal to 10. In my example, when I was showing that, I put 20 here. In this, like, we are padding it with the 10, that's why 10. Okay, so let's run this and see what we are getting. You can see, like, we kind of have like 6 different values. This is what different seniority classes. So we are going to label encode them. One dummy one is always going to get like a 0 index, so that is what this is. And then vocab sizes, you can see 7, 8 and 10, and we are padding to the maximum team size of 10. Okay, so we now have just created like a maximum number. We did not encode it yet, we need to encode it, and that's what this particular section is for. Okay, so what we are doing is we have like we are creating four lists, and we keep on appending the indices of that values, and we kind of append 1 if the number is 1, otherwise 0. By default, m is going to be 0 by padding it like this, right? So we kind of keep on padding it. How much pad we need to do? We need to pad it with maximum team size, which is 10 minus, let's say the first patient had 2 team members, right? Then 10 minus 2, 8. So 8 dummy we have to add. That's why that's how we are adding it here. Okay, so this is that part, and then we are returning this array, which will have like d type and 32, and this is like indices. All of these are indices. Okay, so now we kind of also create dummy variables like length of the entire data set, which is 1222, right? And then maximum team size is 10 10 10 10. Like that we kind of create this XSS, and this is the mask, this is a role, this seniority, sorry, this is speciality, this is the role, right? And this is the mask, right? Mask and all of that, right? And then what you can have is, right, so this is how you can kind of encode and pad. So once you do this, seniority, row, specialty, F means if a specialty, right, because S already came, that's why F. So mask M111, and then outcome 0. So what is this? Is just one example. So this is how the encoding had completed. So once you have the encoding only, so first you need to do encoding, then only you can kind of do the embedding and all. So we kind of now are ready to kind of do train test split. Okay, train validation split. So train test split, train validation split we are doing 80-20 percentage, and we are doing for all of these, even including the recovery variable. Okay, so we are doing even for the masked ones. Okay, so all of them, right? Obviously we have to kind of convert, like divide that into train and test. So we also kind of do like a class weights we don't have to do now since it's balanced, so almost balanced. So we do class weights. Then we move to the embedding, the model architecture, right? So let's build the model. Okay, so this is the model actually. So you can see that we are using a 32 dimensional embedding, like just like how we have seen in the example. So 32 32 32 96. So 5 hidden. So this is like I reduced it from 128. In my example I was showing 128, right? So 128 it will reduce to 64. So 264 layers you can see, we will see that. And row hidden, so this is 64 I told, right? So we'll just move to 32 just to save some time. You can experiment with these numbers. And then input seniority, input role, input specialties. For all of these you can have a different layers, then which we can concatenate all of these 96 separately together. And then you have one mask matrix also, which we will reshape it later, and then we kind of do matrix multiplication later. Okay, so now so you have this layer, so you need to have embedding for this, right? So which will take the so embedding matrix, right? So the lookup which will use the index, and based on the index it will take the embedding dimension, right? So that is what this particular thing is. Okay, so input seniority is nothing but the index basically. So index also it will be length of max team size, which is 10, right? Each one will be 10, and you kind of take that and look up into that embedding matrix. So that is what these three layers are for. Now you kind of concatenate all these three, right? So it becomes 96, 32 32 32 96. Then you kind of pass it through a 5 hidden, which is 64, right? It was earlier 128, 64. Then you add a dropout, then 64 again, and then dropout, right? And then you kind of, once you have this, then that is when you kind of multiply it with the masked output, to so that you can make zeros for those dummy 96 128 64 outputs that you get for the dummy personas, right? So that's why you kind of do this, and that's it. Then you kind of do the reduce sum, you kind of do that. Okay, then you pass it through the 64, then 32 1. So in my example I was just giving you 64. No, I was giving 128 64 64 to 1, right? Now this is 64, this is the input. It goes to a like one more layer, which is 32, right? Row hidden is 32, and batch 1. So batch 1 means one hidden unit there, right? And you are in between, you are using one more dropout just to reduce the overfitting. And then activation function, you use sigmoid, you will use like a binary cross entropy. Here you can see that we will be using that. So these are the inputs that goes as inputs, right? The output is this, and the name of this is deep sets medical problem, right? So we'll compile and train the model, so we'll see that as well. So yeah, you can see that I'm using like focal loss. You can read about this. So this is one kind of loss. So you can also use like a binary cross entropy, anything works here, so you can use this. And you can like now go and fit the model on the training data set. So you fit on this data set. This is the validation data set, right? And this is the Y validation, this is the Y training. Number of epochs is set to 50. Batch size you can put 32, 64, whatever, right? And then you can experiment basically, and you are having early stopping as well. So two kinds of early stopping you have done. So you can sorry, to you do early stopping here, you also reduce the LR on plateau. So whenever you get to see that plateau, so LR is done. So you LR plateau, so the callback will happen there. So you can see the training is happening. You can see that the accuracy of the training data set is increasing, right? So it started from probably like 60s, 59, 60, and it is going all the way till you can see that it is 74, and it has stopped here. 66 is validation accuracy. So it's pretty much it started from, let's say, 51, and then it went till all the way till 66. So I think that is the maximum for this, looks like that, and you can keep experimenting, so you can really increase the validation accuracy. You can printing some of those confusion metrics and all of this part. You can see this you can see the FN score as 66%. So precision recall 66, 65. This is a dummy data, right? So I do not expect this, but still it has come really good. Like you can see 83, 79, 40, 43, 66% F1 score, and precision recall 66, 65. It's not great, but not bad either, right? So you can consider this. And then some more plots. We can see that. So yeah, so first one is loss kept on decreasing. For validation it kind of kept on decreasing, even for the training kept on decreasing, but the gap started increasing with the number of epochs, right? And even for this, for the validation AUC, it improved till a point, then it saturated. But for here there is a lot of overfitting happening, and that's where it has stopped. So since we have put this on accuracy, so it saw that it has started decreasing the accuracy. So kind of it did some early stopping there, right? So but the main important thing is, how do we score it, right? So we have a scoring function also. So we score. So this, let's say this is my team, that this is the team that kinds of does the patient attending the patient. So the senior surgeon cardiology and fellow nurse critical care. So these are the two people. So 44.3% is what the probability is coming out to be, right? So if you want, you can also go ahead and do the recommendation function, right? So you can just do that as well. So you can see, so it's searching for the next best addition. So it will take some time to search and tell, because it is going through all the combinations out there. Okay, so it will take some time. So I'm just waiting for the results. So while that comes, that completes this entire thing. So you can actually search this. You can actually run this, and run this on your system, and experiment on your system as well. Okay, so yes, you can see that the accuracy, by adding this, the recovery probability is increasing 55.8%. So which is very good improvement, 11.5 percentage improvement. So you will ask them to go to this particular person, right? Obviously chief, we had given higher score, probably critical care also we gave higher score, so that's why it came out to be like that. Okay, so that's all I have for this video. Hope you enjoyed this, and you get to learn a lot of things from this. So for more content like this, please subscribe, comment, like, share, and help give me feedback, so I can improve on the next videos to come. Thank you so much.